now I would like to request Professor Manoj C. Paul. So please deliver your first this session on biomass gasification in combined heat and power plants. So please, sir.
So do you want me to share my slide?
Rajan, I think director sir and I could leave the inaugural session because you could continue with the participants for further proceedings.
Yeah, sir.
So,
Yes, sir.
okay.
Thank you, sir. Thank you very much.
Thank you, sir, for running.
Thank you.
Thank you, sir. Thank you very much.
Dr. Manish Paul, and thank you, director sir.
No problem. You're welcome. Thank you.
Thank you, sir.
So, shall I start by sharing my
Yes.
slide? Yeah.
Yeah,
Okay.
here, sir. The top of that right hand side, sir. Yeah, thank you.
Hang on. Yeah, is it better now?
Yes, sir. Perfect, sir.
Okay, just 2 seconds. Okay, good evening or afternoon, everyone again. I'm going to, I know I got 1 hour and 30 minutes on this topic. However, I planned this topic in such a way that I'll have more time on the gasification aspect where we talk about production, and then in terms of the technology combined heat and power, then I'll give a little bit of overview of some of our end-use application like conversion work. So these are pretty much integrated. So it's Manoj Paul from the University of Glasgow. So I'm Professor of Thermofluids. I'm also Deputy Head of Energy Sustainability Research here, and I'm part of the James Watt School of Engineering at the University of Glasgow. So again, I'm very honored and privileged to have this opportunity to give this talk to you. So hopefully you will enjoy my talk. So end of the talk, we can have some discussions or a Q&A session. So moving. I don't know how much you actually know about the University of Glasgow, so I thought I'd just put a few bullet points to introduce my university here. So Glasgow University is a very old university. As you can see here, it was established in 1451. And interestingly, it was the 4th oldest university in the whole English speaking world. And in terms of our rank and reputations, we are ranking 76th in the world. So we are one of the 100 best university in the world. And in terms of the impact, we are really doing great. So 13th in the world and 2nd in the UK. So this is a very large university. So students are coming from almost all over the world here. So around 35,000 undergraduate and postgraduate students in the campus, and we have more than 10,000 staff members here. Within the UK, we have called Russell Group leading university. So we are one of the member of that research intensive universities, and our annual income is approximately 168 million pounds in the UK. So it's a most research intensive universities. In the UK, we have every few years, we do research assessment exercise. So 96% of our work either is world leading or internationally excellent. And we are top in Scotland in terms of engineering excellence. We have 7 Nobel laureates, and I already mentioned James Watt, Lord Kelvin, Rankine, Joseph Black. These are pioneer scientists and engineers who contributed quite a lot in terms of in the subject of thermal energy engineering, or also energy in general application, which actually changed the whole world. So in terms of the content of my talk, so I put a few bullet points so that we know what is actually you're expecting from me. So I'll start with a little bit of background, because it is why this is so important. You need to understand why actually the sustainable energy or something polygeneration of energy, why important. So I should start with a little bit of background with some policy, because you already highlighted that a policy and regulatory framework need to come together. And slowly I'll move to the hydrogen. Okay, so why we need the hydrogen energy and why this is coming as the main sort of energy vectors, and then sources of this hydrogen. How can you get a clean, low carbon hydrogen? And then you'll see my research topic called BECS and BECSS, so bioenergy based carbon capture, utilization, storage, through which we are aiming to get biohydrogen productions. And this is also a carbon neutral or net negative emissions. So this would be kind of the first part. And then I will give you a bit of overview of some of the research that we have been doing within this thermochemical or gasification area, where I will be targeting to get more hydrogen and this biogas from this. This is basically part one, and that might take me more time than the second one, because second one will be utilization, so conversion aspect, and what sort of challenges we have. That's why I thought we put part one and part two. If you after finishing part one, if you need a couple of minutes short break, we can have, but I can continue. Then I'm also part of this UK's flagship project called Supergen Bioenergy Impact Hub. This is funded by the government, a £5 million project is actually looking towards the application and impact of bioenergy within the whole sort of energy network, and where I'm leading a work package which is actually targeting negative emissions from waste and hydrogen BECSS. So some of the things we are talking about will be part of this project as well. So in terms of the policy, let's start with this international policy. This is nothing to do with the UK. It's true for all the countries in the world, including India and UK. So we know that the Paris Agreement that we had in 2015, December 2015, and then every year in the COP, this is discussed and then reviewed. So in terms of the impact of global warming, I don't need to spend too much time. We know that there are a lot of catastrophic events happening. Just the one you saw a few weeks ago, the fire in LA in USA, and there are a lot of flash flood and other things. These are continuously happening, okay? So which means that we really need to get the global warming temperature down, and then from the Paris Agreement we understand that it is identified to be 1.5. And then we have another international sort of policy framework which is called Sustainable Development Goal. So we have by the United Nations, we have 17 goals. And interestingly, we are more sort of thermal energy and the energy people, and number 7, as you know, is actually talking about affordable and clean energy. And other are pretty much integrated to this. One of the things I quote from here is pretty much copying from the Sustainable Development Goal statement that energy is central to meet some of the other essential goals that we have, particularly social aspect, economic, environment aspect. Therefore, we need to look into how we can actually provide an affordable and clean energy. In the UK now, we have a number of policy documents recently published, but these are the highlight. I don't need to actually go through all the details here. I'm just going to talk about a little bit briefly about what we mean by the net zero. So UK's target to get net zero by 2050. That means whatever emission we generate, it needs to be neutralized. That gives the zero by 2050. And this is calculated based on the baseline called 1990. And the next slide, you'll see some specific details about called 6th carbon budget. So it means every 5 years we get the carbon budget. And it suggests that by 2035, which means just in less than 10 years, we need to get 78% greenhouse gas reduction. In Scotland, this target has been reduced in terms of the year. So we want to get by 2045, 5 years ahead of rest of the UK. And European Union has the same sort of target that getting net zero by 2050. These are pretty much the policy documents here. Now, this is now number, so it gives you good sort of feeling and understanding that when you're talking about really carbon greenhouse gas emissions in terms of the number, what we are talking about, okay? So here, this is CB1 to CB6 carbon budget, and these are the scale of the emissions, and you can see that there's the solid curve here, the CO2 gas falling. These are actual data, and the dash indicates the projections, okay? So if we talk about by 2035 CB6, so if you see this, get some understanding what sort of number of the CO2 we need to get is basically is nearly 1,000 metric ton CO2 equivalent, okay, that we need to reduce based on this 1990 target in order to get 2050. So as you see here from the UK perspective, so the trend is quite good, and we will have another sort of projection of carbon budget shortly this year. Now, one can ask the questions, why do you get all the emissions from? Okay, let's look into this chart. Although this is generated in 2018, but this is generally the case if we take the data recently. So if you look into this chart, so you can see that most of the emissions coming from heat, because UK or Scotland is kind of the cold country, we use a lot of energy in order to warm our house. However, this heat is not just the space heating, it has industrial processes involved as well. So industry manufacturing processes that require quite a lot of heat, like steel industry, a lot of heat. So you can see here about 40% emission coming from heat. And then the second one is transport, 30%, okay? Car driven by fossil fuel, plane, and also the marine sector. So they're all together coming in the transport. We got uprise in the electric car, but it's still, this sector is dominated by the fossil fuel, and some other things are there. So in terms of then, I feel this is quite interesting also, break down the emissions sector-wise, and then you can clearly see that some sector are actually doing great and some sector are quite challenging. One of these sector is transport, as you can see here, the purple one. So this sector is very difficult, as I said, is actually decarbonized, and also if you look at the orange is a building, so heating. So how do we get low carbon heating for our home and for our industry? So these are kind of challenges we have here, and some sectors are doing great. So as you say, the target is to get down to zero by 2050. That means all these sectors need to actually find innovative solutions for that. Then there are some other policies, and these are very important for my talk as well, because UK said in order to reach the net zero, that government identified 4 priority area. That's, we say, 10-point plan. So that was published during COVID, and that linked to some of the strategy called biomass strategy and UK hydrogen strategy. So of those 4, I have bioenergy, I have hydrogen, CCUS, and also industrial fuel switching. So from fossil fuel to low carbon fuel. And home, so basically talking about the heating aspects. So these are pretty much interlinked. So my topic today will focus on bioenergy, hydrogen, and some of these also CCUS and industrial fuel switching as well. Then I talked about this bioenergy policy, but this is also an important policy from the UK, from the hydrogen strategy that's published a few years back. This is still live. So if you just look into this graph, so in terms of getting the net zero, what is actually UK targeting by 2050 is saying that about 500 terawatt hour, or between 200 or 100 to 510. This varies, but if you see the norm here, so between 4 and 300 terawatt of hydrogen are expecting to be in the energy sector. And then if you then find a distribution percentage of energy, is saying that between 20 to 30% will be needing or using this hydrogen. There's quite a lot of demand here. Okay. Then I found this is also interesting, how this synchronize globally. So if you see here globally from 2020 to 2050, this is also exponentially rising, the demand of clean hydrogen. Okay, so this is synchronized to the UK policy as well. And then you can look into this breakdown of the sector, which sector thinks will use more hydrogen than other sector. Remember, I mentioned about the transport. So transport thinks that, okay, they need more hydrogen because they are struggling, they're hard to decarbonize sector. They think that if they can bring hydrogen into their systems, therefore they could minimize the carbon emissions. So they think that this is possibly, that's why you see the number increases. And this is global, not in the UK. And other industry building sector are like this. Then, before we set the scene also, one can ask the question again, okay, what is the current state of this hydrogen production? When you talk about the hydrogen production, how do you get low carbon hydrogen? From where? Where's the source? So worldwide, also this is true in the UK perspective, if you look into the distributions of the production of hydrogen, you'll see that more than 90 or 95% hydrogen that is still generated from fossil fuel. Either is coming from coal, from this gasification, partial oxidation, then you liquefy, and also you have called steam methane reforming system. Okay, you use natural gas and then you reform, you get hydrogen. These are typically the case internationally, globally, and also in the UK to date. However, there are a lot of investment happening in the UK in order to get green hydrogen. So I'll just briefly talk about this biomass here. There are various options, as you see, that hydrogen productions. It can come from wind, solar, natural gas, biomass, and these are the conversion to hydrogen. So of those, biomass is fantastic vector because it can actually take several pathways. ATR, Advanced Thermal Reactor System. Then you have SMR, so something, if you go biomethane, and then you can actually get hydrogen from it, and you can pyrolyze it. You can also use gasification system. Depending on the feed, there could be biological systems. So it's an important vector for this, right? This would be kind of the last slide for the introductory part, and then I'll move to the core research content. So I think when you are looking into this hydrogen color, so I think almost everybody listening to me is aware of this. The hydrogen comes with a different color. So if you use natural gas, you produce hydrogen like steam methane reforming, and CO2 will be released because of the carbon there. If you don't do anything, then it becomes gray. However, if we have a technology called CO2 storage, then it's the same process, but because it's storing CO2, therefore it says a kind of blue hydrogen. But remember, the hydrogen is still coming from fossil fuel. So this is called green hydrogen. So we got green electricity, whether it's coming from solar, wind, and you break down water and then hydrogen, and you got oxygen releasing, but that oxygen could be used for other purposes. Of course, we need to make sure that we have some, because electrolytes are very expensive. They're sensitive to water, purified water. Therefore, we need to make sure that it's a good quality water. And pink hydrogen related to your, if you use, what's it called? Nuclear energy, then is pink hydrogen. Gold mean is solar. Right, so my topic is, I would like to demonstrate a technology that could actually meet the net negative emission hydrogen criteria under the BECCS context. So let's give you a brief overview which way we are thinking to design this concept. So we have, say, municipal solid waste or biomass waste. Municipal solid waste can come with different sort of variety in it. I'm talking about all non-recyclable waste, where biomass would be mostly involved there, but it could come with plastic and other things. We choose a thermochemical process. Depending on the feedstock, it could be another sort of processes. So whether we do pyrolysis, we do gasification, I do both in the combinations, you'll come with called syngas. Within the syngas, you of course have a filtering system. We normally use PSA here. Then you can get hydrogen out and then CO2. We got two options. A, if you sort of capture it, or one step you can utilize it within this process, so we call CO2 gasification, then you could get more sort of high caloric value of syngas, and then also this could be used for other utilization processes. So in order to meet the net negative, so basically the CO2 absorbed by the plant, if you see the CO2 remains within the system or trap it, so that amount will give you the negative number. And in terms of the techno-economic aspect, it suggests that if we can design and operate a system like this, hydrogen could be cheaper than what we get from electrolyzer, but it depends on various other things, okay? Material use and feedstock use and everything. But if you look into the SMR, the coal gasifications there, and the biomass gasification hydrogen, they are very close, but that is the data published few years back. So I think that is going to change because of the economic aspect of everything. So let's start with the questions, okay? What are the challenges we have in order to make a technology that could provide us the net negative hydrogen? You don't need to read all this bullet point here. Let's look into nice pie chart. If you are doing gasification, and you possibly know this, if I have air gasification, okay, right. If I have air as an agent for a biomass to be gasified, then typically you will get about, say, 50% nitrogen, which is no use. Then about 20% will be hydrogen and 20% would be carbon monoxide. These are my gas component, carry quite a lot of calorific value. Then you might have some percents like 5 to 10% CO2, still biogenetic CO2, but this is CO2. And then you might have a little amount of biomethane there. So this is typical gasification results. But my goal is to actually increase this portion of the pie. So from 20% to go the way I like. So the question is, how can we maximize this? If we want to maximize, which means I need to minimize some of these components. So that's the questions. Then whether I switch from my gasification agent from air to oxygen, CO2, or steam, what sort of impact it will have. So you have the diverse options of choosing the gasification agent. Then the question comes, some of the feedstock that I'll be dealing with, they are not typical biomass. There will be lots of non-homogeneous material in it, like municipal solid waste. I'll also demonstrate some cases where you'll see that we're using agri-waste, okay? That comes with a lot of ash content in it. So how are you going to deal with all this? So you need to start the fundamental study in order to look into all this, where you will see that a lot of chemical kinetics need to be studied. And one of the things is still challenging is called tar contaminations of the gas. How could you actually understand better so that you can actually minimize this? And then also within the BEXAS context, when you go system integrated together, CO2 needs to be somehow utilized. That's my concept, utilized. Therefore, you also need to find a way to actually optimize the whole system. That brings your title called polygeneration. So how could you use some of the waste heat in order to maximize the production and improve efficiency? And what would be the design aspect of a gasifier? So these are the questions I have. Let's see now in the next few slides if I can give you some of the overview of those sort of points so that we see how we are dealing with all this. And this was part of some of the research that I'm going to result I'm going to show part of my fellowship that was funded by Royal Academy of Engineering a few years back. Okay, so let's start from the basic. So is gasifier, you can have different types. This is just say one example here. It's called downdraft gasifier. Typically, if you have feedstock feeding from top, you have a drying zone. So gasifier feed will be dried, and then that goes to the pyrolysis zone, and then you combust it. So that's called oxidation zone, and then is the reduction zone through which the syngas is actually generated and left. Now, if you look into the chemical kinetics of it, so this is the first step because it's basically drying, and then the pyrolysis zone is quite interesting because after drying, it actually goes through three phases. One is C, actually char. You might have some small gases, and then the another one, basically the tar. Although sometimes people think that I got the tar contamination in the syngas, that's very challenging for downstream application, but tar is actually generated from the pyrolysis zone, not in the reduction and the end use zone. Is basically sources there. So you need to look into its behavior, chemical, thermally about this. So I just used a benzene format here, but later on you'll see that we are going to amplify this and look into all the kinetics there. These are also typical kinetics where you can see that gas phases, and then most of the kinetics in the reduction zone is basically called non-homogeneous kinetics because we have solid phase char. So these are all together need to be solved, and each of these is controlled by its own chemical kinetics. So we developed a kinetic code in-house in order to address some of the challenges that we're talking about and to see how we can optimize the gasification processes. Going back to this, so we started with this benzene. However, very early literature published in 1994, I found this one very fascinating because it talks about that when you look, take a sample of gas or even in the tar in one of these pyrolysis zone in the reactor, depending on the retention time, this is called chromographic data, so retention time, these chemical species can change from one to another. So start from benzene and you can see the 1, 2, 3, 4. These are just the name. Although it just 23 is there, however, later on you'll see that there are more than 20. There may be hundreds of chemical species. They are actually transforming from one to another. So these are basically the source of the tar. Another thing is that one can say, okay, let's fix the gasifier condition at a given equivalence ratio. Let's take a sample at one of these point retention time. However, then if you look into because gasification inside temperature is basically also non-uniform. So depending on the temperature, their fate could also be different. So they can change from one to another. So there are two key aspects, temperature side, although fixing equivalence ratio, and also the retention. Then what we thought, okay, let's have a look into the non-uniform distributions of the temperature, which is basically thermal field in the reactor. And you can clearly see that temperature is not constant. So depending on the feed, depending on the moisture content, we can clearly see that we have variation of the temperature in the system, which means that we then expect the variation and the fate of this tar species in the reactor. Then similar experiment we did. Sorry, I'm just drinking a little bit water. So we did a similar sort of experiment, GC analysis, in order to look into all those components, as you can see here, based on the retention time. So these are we can do, but the question comes when this component changes from one to another, how can you actually write a code that you can actually take all these reactions, all the chemical species, and all these kinetics? This is very challenging. So we extended our code from typical chemical kinetics where the tar species are included, and that paper is very well taken, was published by Biomass, is basically showing the evolution and the formation of tar. Okay, it's just not the downstream, it's basically coming from the source. And then that gives us plenty of opportunity to look into this tar problem from a very sort of different perspective. Why? Because one can actually now look into the behavior of species, how they actually change from primary phase to secondary and tertiary. What are their names? Phenol, toluenes, naphthalene, benzene, but they are appearing at a different stage and based on the different time and also along the gasifier there and dependent on the moisture content. So it's just not the one number, different phases and coming in the different stages, and they are highly non-uniform and non-linear here. And then we did some further experiment just to verify some of our findings. And the first study we did with colleagues in KTH in Sweden. I think you possibly know they're fantastic colleagues there, very good university. And we did some experiment there, but in-house in Glasgow, I have similar sort of experimental facility now. Then we look into this model prediction and then the experimental result. As I said, mostly in the literature, you'll say people just showing total tar or even benzene. However, this is kind of the data was very, very useful because it gives you the breakdown of the component of tar and how the kinetic model predict, and then we validate this with this experiment. Okay. So that is coming from the reaction level, okay? So these are my kinetic model. Now, the second phase, we are looking into the reactor level optimization. So let's see the same sort of reactor. If we are interested to look into more sort of design aspect, thermal aspect, and everything, how do you do that? That's obviously called computational fluid dynamics approach. And I think you are familiar with this. So how do you do this? So basically, we get feedstock, we decompose it, and then these are the kinetics coming from my kinetic model need to be embedded into the code, okay? Combined with hydrodynamics and also other like a thermal transport needs to solve simultaneously together in order to predict the thermal field and the gas field inside. So in typical commercial code, you will not see this sort of thermochemical kinetics. So that is our sort of in-house developed code. So we write a lot of code inside this. If we use commercial software, we actually make a subroutine and then integrate to the code in order to predict the behavior there. This gives us another opportunity to look into more details. For example, although I just horizontally put this gasifier there in order to check the reaction kinetics. Remember the drying and pyrolysis, where we know that devolatilization will take place. We can pinpoint the rate change coming from the devolatilization, and I can clearly see that peak is there at that zone. I don't expect that peak to occur there, and which is proved. I can look into some of the oxidation zone kinetics like this, and I can put the reaction rate. I can clearly see is operating there. And also some of the reduction rate, chemical reactions like Boudoir reaction, they are triggering at the reduction zone. So which actually give me the full confidence in my code development. However, depending on the problem, depending on the feedstock, some aspect could be quite tricky, because when you talk about kinetics, you need to rely on a good set of kinetic parameters. And literature is sometimes really poor, because sometimes you see that you are getting a set of kinetics, but they are not based on the condition you want to operate your gasifier at. So there might be different thermal condition, maybe different pressure. So sensitivity analysis is very, very important to actually look into the impact of the variation that you see in the kinetics and how they influence your prediction. So it's here, I can see here, experiment is this one, and the kinetic model is the orange one. And some of these are only for these single or two reactions, but variation in the kinetic properties, they could actually influence your prediction. So we did some sensitivity analysis coming from the kinetic analysis as well in order to identify a good set of kinetic that gives very close result close to experiment, that's temperature and also from the gas species. So again, some data published here in this renewable energy journal. So this is kind of the final from the story. So we got kinetic data, we now have CFD modeling, we now have experiment in order to couple everything together and also verify with some of the benchmark data from literature. As you can see here that we got reasonable good agreement here. Now I put a dash sort of elliptic shape to mark here that remember the question I asked, the hydrogen production. Still, the problem is I got about 20% hydrogen. So that same story because all this experiment and the model done based on air gasification. So then we'll come back to this point. Then I thought, okay, if I change the typical feedstock from typical biomass to some unconventional feedstock like waste coming from, these are agri-based waste coming from various farm in Scotland. I believe that some of these waste are familiar to you as well, especially straw and other things. They are very much you can get from Indian agri-sites. So what we have done here is some, obviously, if you do want to understand this energy content first, you do ultimate analysis and also proximate analysis just to see the behavior of this sort of feed. So some feedstock carbon content vary, but what happens is that some feedstock, their ash content is quite high. So we have to be really careful to put these in a reactor because ash, as you know from the theory, ash could melt and it can actually also damage your reactor and block things. So basically you have to be very careful to handle with those sort of feedstock. So what we have done, we choose some of those typical feedstock and then we did some modeling, CFD modeling, and also a few years back we have done some experiment on the sort of downed-up gasifier, a 20 kilowatt gasifier experiment. So I'll show you another pictures shortly that about the new sort of experimental rig that we have in the lab. But based on this, we can see that some of these unconventional feedstock we can use for gasification. But again, if we talk about hydrogen production, we are about 20% because it's air gasification. Now, in order to enrich hydrogen productions, because we understand that there we got a lot of nitrogen. If you go back again there, remember that is 50% nitrogen. One can say, okay, if I reduce this nitrogen, can I improve it? Okay, that is the theory. So which means I'm going to move towards, so first case, moving towards oxy. Okay, so reducing nitrogen content and improving oxygen in a reactor and try to see the impact. So A and B, A is classic air gasification. Under same conditions, if we are doing some oxy gasifications, and I have highlighted here the hydrogen production that, okay, we can range from 20 to 30 to 35%. Why? Because oxy gasification it gives you more sort of thermal power inside, so temperature inside the reactor raises, and which means that can actually break down some of the hydrocarbon, also the tar within the reactor, and some of them could actually convert to hydrogen. That's the benefit. Then that's a good message. However, we can improve that a little bit further as well. How? This Z means the changing in the throat of the gasifier reactor. So if you constrict a bit more and then increase the retention time, then there's a way that you could also try to improve. But we can get up to 30 or between 30 to 40%, which is promising. And then we thought, okay, now I know that steam gasification is still the best one, so we did this various way. So like high temperature steam gasification, some autothermal and high temperature air gasification, and we also brought in some solar input in order to actually improve the energy aspect. That is also part of polygenerations, because you need to have energy in order to get steam as well. So if you get this from other renewable sites, so that might give better sort of understanding and also the better efficiency here. So what we can see here, that if we look into the blue one, dark blue one, this is possibly the best one still we have. So greater than 50% we can get. So this gives me some sort of understanding that, okay, if we move towards steam gasification, there might be a way that I could maximize the hydrogen production. This is just one picture coming from my lab, but I'll have another one shortly. So how we actually used our design our reactor in-house. Then, okay, another thing is within this aspect of CSP, combined heat and power, and then how to also talk about net negative in CO2 emissions. Again, within this novel BECCS concept, so what we are thinking, I'm going back to my drawing. When you have gas separation from it, you can chemically think that you can use a dry deformer for this CO2 combined with some remaining methane to get syngas, or you can take this CO2 back to the reactor. And if you got the downstream engine here, for example, that could give you power and also maybe heat, then the CO2 coming out of it, you can also try to put that back here. So I'll show you some results, but this is basically the idea of this net negative BECCS CSP. So it's possible, but there are challenges. Suppose some results. Fixing the gasifier temperature at given, say, 1000 Kelvin, we can clearly see that now how much do you want to take? Depending on the recycling of CO2 at the ratio, you can see that, yes, some changes we can see in terms of this gas production. But if we are talking about hydrogen, so red color, we don't gain much, okay? There are some equations, particularly this one, that carbon steam breaking down to hydrogen, and this is promising one, but it is very sensitive. And the variation of this thermal in the power in the gasification could also lead us to some negative emissions there, but it's a net negative, okay? Then we look into the overall efficiency, because you cannot just take CO2 away there, because this is sometimes called endothermic reactions, need to have more power in order to operate. But at a reasonable conditions, we can also see that we can maintain or in some aspect improve the overall efficiency as well, okay? So lower heating value is slightly increasing because we are producing carbon monoxide more, may not be hydrogen that much, but overall they're in the good directions. Then from that one, this is the system level, and we then developed a BECCS full cycle here. That's a paper that we published recently, but I'll show you the system design first. So this is, I know it's super complicated, but let me just break down this one. So here, the first bit, left-hand side, the gasifier unit, you have the production unit. In the middle, you have the cleaning, and then downstream, you have an engine. So this is basically a CSP, bioenergy-based CSP, where you also have the exhaust stream shown here. Some of them are recycled to the gasifier. That's why it's kind of the BECCS cycle. So this is sort of mathematical form. We haven't done any experiment based on the whole concept. The things are moving, and then we are developing a lot of things accordingly. Okay, so therefore we have a lot of opportunity to actually look into this. But we got some results, good results are published within the concept of these BECCS. So feel free to please read some of the papers there. Now, I think in next 5 minutes, I'll just finish the first part.
Excuse me, sir.
I know that, yep.
Can you show that paper, sir? Once again.
Yep.
Which you have published in ELSAL, sir. Can you show that topic name? Energy.
Oh, energy conversion and management.
No, sir. I want to see the paper, sir.
Do you want me to click on this?
Previous slide, sir. Just
Oh,
previous.
right. Okay. Yeah.
Yes, sir.
Okay.
This one.
There are two papers. That's the first one, and then the second one also there. So it's 2022, and that's 2023. Okay.
Okay, sir. Okay, sir.
Thank you. So I'll move on. So as I said, I'll have just maybe 5 more minutes to finish the first part. So we are moving from typical biomass to agri-waste. Now we are thinking about municipal solid waste. This, as you see here from this picture, that this is not biomass, 100% biomass. You got quite a lot of, we say rubbish, they got a lot of other things. You got plastics, you got maybe foods, you got clothes and everything. And from the World Bank report, if you Google, you can see that they say that about 4 billion tons of waste are generated every year. That's the worldwide. Of course, that country to country, this can vary. The problem is the vast majority of these waste are disposed, okay, and whether in landfill or typically combusted, okay. So that is a lost opportunity here. So we are thinking that how we can actually use some of this municipal solid waste to hydrogen or even the energy generation efficiently. Then one thing we did, we look into a typically called food waste, okay. Then we did try to understand, remember we talked about the kinetics, because some kinetics are based on standard biomass and based on also coal, especially the Boudouard reaction where carbon is there. What we did, we first took a sample of food waste, and then we did thermogravity analysis, and we also generated char from the pyrolysis unit. When you look into the char chemical composition, you will be really surprised that char composition you get from typical food waste is different than another char you get from, say, biomass or even coal. Therefore, I think there's a bit of contradictory message here that in the literature, if you want to use some kinetics based on the Boudouard reaction, based on a typical sort of biomass or coal, in the process of waste, then I think you fundamentally make a mistake here. Therefore, what we did an intensive experiment and also theoretical study to actually generate a new data set for the kinetics of a given food stock. And you can see here that some of the kinetic data, and that was published in Energy Fuel, and which means once you want to develop this model further, you should be actually use some of the data to actually study this. Which means also that if we vary feedstock, which means that we also need to look into this chemical kinetics very, very carefully before even start modeling. This is a picture taken a few days ago, so it looks clean lab, but lab is not always clean like this. So we have a pyrolysis unit and gasification unit, and you can see here we're using a furnace-based system controlled by various so mass flow controller and the downstream syngas cleaning, syngas measurement, everything. So idea here, when you have this flow loop going on, we should be able to demonstrate the BECS concept as well. We should be able to look into the utilizations of CO2 back to there. This is one of the furnace, but that furnace is quite good. You can actually change the orientations of the reactor. And remember the other one we said downdrop gasifier is actually sitting somewhere in the corner there. Okay, so that means it's also operational. Okay, and there's just some other result that if you have a good control in this experiment, you should be able to simultaneously generate 3 phases of energy, starting from typical syngas, and then also bio oil, and also biochar. And later in the talk, I'll show you that we have the diverse option of utilizing biochar, but this is also a kind of controlling the whole process in order to generate 3 phases of energy. So this is the first part of my talk, which basically I talk about more sort of production aspect, and then also highlighted some of the bio hydrogen. So, and then part 2 might take about 20 to 25, 30 minutes, but do you want a pause for a couple of minutes, or you want me to continue?
Please continue, sir. Please continue.
Continue, sir.
Great. Okay. So this part, so we have been also doing a fantastic work in terms of end use of hydrogen, not only hydrogen. You said hydrogen blend fuel because it's basically syngas. You have carbon monoxide, you have methane, you have other things. So how could you use those sort of new types of fuel that will be more sort of process dependent? So every process alteration you have, you saw previously that the composition of gases actually also changes. Then if you have a downstream applications, and then we're not talking about a fuel cell here, but if you typically burn it, you have quite a lot of challenges, and I'll show you some of these shortly. To introduce, I found this sort of diagram quite useful coming from Hydrogen Council, so international bodies. So you have hydrogen production. So this is electrolyzer here. So I talked about the biohydrogen, so quite similar production, and then you then have distribution. Okay, so there are also a lot of challenges how to store and distribute hydrogen. So we are not discussing this here. This right-hand side is basically the end use. Of course, end use is, I find it quite interesting because it's divided into several sort of sector. So transport, it varies, as I said, decarbonization transport. So we can use hydrogen. You have industrial sector, and then hydrogen and other feedstock could also be used as a feedstock for chemical companies and also buildings. Remember, we said heating is required by buildings, so there's a way that that's also called CHP there. So there are other technologies, as I said, maybe fuel cell are used, and there's my main objective here to look into the typical combustion challenges, okay, under the CHP. So this is a busy slide, but I'll take time to explain this. So moving forward, when you say I want to, let's say 100% hydrogen or even ammonia, people might think, okay, we do not have any emissions for my downstream application because this is carbon-free. Hydrogen is carbon-free, although we are not talking about the production side. Let's say hydrogen is given. But if you are familiar with combustion, you know that if you use air in order to combust it, you will have to deal with quite a lot of NOx emission. This is another greenhouse gas. You cannot avoid it. So my research questions start with this objective. If I move from typical non-hydrogen to hydrogen fuel for an engine, I have to deal with NOx. What is the best way to design a reactor and operate a reactor so that I can go very close to zero NOx? So that's why I put ultra low to zero NOx. And we are working on a catalytic combustor. So in the right-hand box here is basically design a lot of chemical modeling that we have been doing here with an aim to get NOx very close to zero. So in the next slide, I'll show you a little bit details about the modeling with just the introduction here. And we also are looking into the conversion of the catalytic hydrogen and experimentally. So we got a tiny reactor, is a U-tube type reactor where there you have the catalyst and you have the high thermal imaging camera in order to look into the thermal spot, because it's sometimes hydrogen burning inside is very difficult to see because it's invisible, you know, so you need a sort of infrared camera to actually trace this. And also we are looking into various other designing of the combustor, because we are trying to blend with ammonia. These are another sort of challenges here. Ammonia in one aspect is better for storage, but is significant challenges you have in combustion, because you have the very narrow threshold for combustion's flammability. However, if you look into this chart here, NO per ppm and also versus equivalence ratio, you can see that at very low equivalence ratio, so that means we need to operate combustion system under lean conditions. There's a way that we can actually kill all these NOx. However, system will be very unstable. Okay, I'll show you later on as well. So these are the challenges we have. So we are combining experiment and also modeling technique together to understand some of this catalytic behavior of hydrogen and other fuel. This is the paper 2025. That means it came a month ago, and I really like this paper. This is the first sort of paper looking into a catalytic, which is basically, see the new burners, stagger type burners, where you have cylinder red basically coated with platinum, and then you have hydrogen injected through the channel. So you are looking into these highly complex chemical reactions. It's actually happening around the surface of the cylinder, then reacting with hydrogen, which is homogeneous reactions, and then you have the reaction kinetics coming from NOx, and then you also have conjugated heat. I don't think system can go any complex than this. Okay, these are really, really complex. So, and then you have the turbulent flow behavior. So you're looking into the application of large CD simulations, and then see the whole behavior, and with the goal to optimize the amount of catalyst that we use in terms of reactor, because platinum is very well known and everybody knows that is very expensive material. So therefore one can ask the questions, what is actually the minimum that you can use in a combustion reactor? And some of the results that we found really fascinating, because it's completely coming from the fluid mechanics perspective, and that is also linked to the polygeneration, how best you can actually utilize some of these fluid behavior concept that will be applied to the design of a combustor. So if you're interested, I encourage you to just read that paper, please. Then
moving train, we see that मम्मी जी मूंगफली कह रहे हैं, मूंगफली ऊपर से ले लेना, ऊपर रख.
Yeah, please mute yourself, please, participants.
इन्हें खोलिया होगा
I'm
अक्षित.
requesting, yeah, everyone.
Yeah. Okay. So, right. I mentioned about if you are working in this hydrogen energy area and the applications, there are various things in addition to the NOx, the various fundamental things that you have to deal with. One is called the instability of flame, because hydrogen flame quickly can be unstable. That's pretty much known. And also the challenges is if you go blend of hydrogen with other gases, which is you have more challenges to deal with. I'll show you some of the nice results starting from a very well-known diffusion burner operating under laminar condition, because you're looking into the instability. But in a turbulent conditions, you have a different sort of instability that is already dealt and showed you in the previous slide. So I put some bullet points that hydrogen flame are susceptible to the different instabilities. This could be thermal expansion, coming from thermal expansion, and some of the things I'll show you could come from the buoyancy effect. And that can cause flame flashback and the blow-off situation, and basically is combined with thermodynamics and thermofluidic and physical chemical effect can actually destabilize everything. So it started with some basic understanding and published few years back in hydrogen journals, look into the composition of various in the syngas, and how the flame itself become unstable, and what is basically a sort of mapping exercise we have done. So I'll show you some nice results. So start from basics. What is actually stable flame in terms of this diffusion flame concept? Okay, a stable flame you find and sort of undisturbed, a nice sort of shape like this. And of course, natural gas burning in a combustion chamber like this should have a flame shape like this. Very nice, okay? Because it's operating at laminar condition. Remember, we are not pulsatile, or we are not generating any turbulence. Very simple. However, if you think now you're putting diversity there, so diverse options, syngas, producer gas, and comes with the various sort of compositions, you can see that combustion performance is going to change because the flame shape is going to change, and hydrogen is there. So if your flame shape changes, obviously you expect the thermal power coming out of it as a heat is also going to change, but this is a classic stable flame. Now, in terms of instability, this is one nice example and very good, and this is called the intrinsic flame instability. So I can explain quickly and show you some results. So this is stable, so flame remain like this. In some situation, a flame could flick, so it's tried to rise, but it doesn't go above that point, and then it come down. It doesn't go above the point like this. And sometimes flame could oscillate. It's called the tip cutting flame. So flame going up, then it will cut the tip, and this one actually detach from the flame and then leave. And then it goes like this. So there are three scenarios we are going to actually study here. And this is part of called intrinsic. And this is animation coming from our modeling study. And I'll give you a few seconds so that you can basically see those three behavior. Okay, this is highly resolved time-wise simulation, and also spatial, because in order to generate an animation like this, you really need to save a lot of data. So this is, as you see, is based on time, but it's still the stable flame on the left. And the middle one called flick flame, you can see I put a line there in the flame front, is going up and then it going down, okay? It going up and down. But the third one, you see the flame, okay, going up, reaching there, and then reaching there, and then in the middle, it cut the tip, okay? So that's so-called tip cutting flame. So the reason I'm doing here, because I'm saving the change of this tip, okay, cutting. So that's why I put H, maximum minimum tip cutting of a particular flame, and saving this data with time, because later on I will look into is a spectral analysis and frequency factor or frequencies factor, so that I can actually understand the core fundamental basis of all this. So again, stable flame, you see a horizontal green line, and then you have red dot, basically a flick going up and down. And then you can see the solid, but blue one, maximum tip cutting, and where you got tip cutting positions, and also the minimum tip based on the drawing. So now we are converting all the time domain to frequencies factor, and this is also very interesting. Why? Because I put in the vertical axis the flickering frequency, and then the horizontal axis flow rate. So we are going to vary the flow rate. That means we are going to change some of the equivalence ratio here. And all this data you see based on the compositions of the fuel. So we started with CO2 rich fuel. Equi means half CO, half hydrogen, pure hydrogen, hydrogen rich, and all the syngases. So red indicates when, how the tip cutting occurs at what frequency, and blue indicates the flickering. So basically, these are highly dependent on the flow rate and also the flickering frequency. That gives us another way of looking into the impact of this flame, because in the y-axis I have dT, which is basically change of the temperature based on this oscillations frequency, how much changes you actually see from the flame side, okay? Because that would be converted to the heat transfer that we need for my CHP later on. However, we can see that because of these oscillations, I can see that large portion of my thermal field actually oscillating because of the delta T, and that are dependent on the flow rate. If I convert these to the heat release, the chemical heat release, quite important for the heat getting from it. As you also see, this is not typical heat. This is basically change of heat in terms of what happening because of this flickering or other phenomena that we explained. So, which means again that a burner could easily get destabilized because of this oscillation, even at a reasonably low Reynolds number. So we then produce a nice sort of map in a tabular form. T here indicates this, okay, S is a stable state, F is flickering, and T is tip cutting. So basically you can see in a stability study, sometimes these are also put graphically, that you find a sort of optimum marginal zone, and then you actually break down the data. So we thought, okay, we produce this in tabular form so that see under which condition you can find these changes. And then from there, we looked into the critical Reynolds number based on all this fuel and based on also Reynolds number. And Reynolds number in y-axis is below 160 or even 300 because we are still talking about laminar flame. Why this is so important? Because it gives me a clear summary of the flow rate converted to Reynolds number, and then what sort of Reynolds number. Maybe if you change the Reynolds number, then this behavior will completely change later on. But this is coming from the stability map, therefore this is quite interesting. These are also fuel dependent, as you see here. At some fuel, at some condition, you might get higher Reynolds number for this critical, and then some not. And again, these are all published in Hydrogen Journal. Then just a few more slides, I'll finish. This is another nice piece of work that we published last year in Hydrogen Journal again, and another reputed journal. Asking, because there's a sort of policy going on that, okay, if you switch fuel from typical hydrocarbons, say methane, to hydrogen, so you cannot jump to 100%. Of course you can jump, but if you do a gradual change, okay, then how do you actually look into is a change in the emissions in the both sort of perspectives, CO2 emissions and also NOx. So this is a summary coming from a typical sort of premixed combustion system, which are usually used in industry boiler or even house boiler. So these are very useful information. So left-hand side is 100% methane and right-hand side is 100% hydrogen. In between you have blend, so 10%, 20, that way like this. We operated the burner under 3 different conditions, make it 25% excess, so provide more air and then some more air, more air. Some results feel to me obvious because if you increase air, you are getting better combustions, therefore you gain CO2, and at the same time, because thermally it will get a little bit less thermal, therefore NOx might reduce. However, if you then combine together, so one is going that way, one is going that way, then what is actually the optimum? If you move there, you don't get CO2, but you're getting your maximum NOx. Here, you're getting maximum CO2, some there. So then, of course, this data help, whether for designer or engineer, to understand what is actually the point you want a burner to be designed in order to meet certain conditions. And this is not linear, okay? This is highly non-linear behavior. So that means 20% reduction or increase in hydrogen doesn't mean 20% reduction in CO2 or 20% increase in NOx. This is, as you see here, highly non-linear. Like 2-3 slide finish. These are coming from a different perspective. I know this is not combustion, this is polygeneration, but under polygeneration topics where you can see some of the waste char that we generate from waste feedstock. We are actually using this feedstock in a different way. One of the applications here is this, how we could actually combine this biochar with phase change material, make a composite, and then use this for low thermal application like solar energy that we have. Why we are doing it? Well, you possibly know phase change material, some of the typical phase change material like wax, they have a thermal conductivity which is not great. So if we can improve the thermal conductivity, hence you should be able to improve its thermal capacity at the same time. Then when phase change material you use in applications for storing heat, when it melts, as a possibly that it could leak from the surface, from the system. Then biochar gives you another opportunity to prevent leaking because it is a porosity. You see the porosity then. Then the liquid of this PCM moves through all the pore. It actually finds a trap for that. On the other hand, biochar is primarily carbon, so it has a better sort of thermal conductivity. So you will be winner from both sides. But there's a problem that biochar could come from different sources. And as you see from my in my lab, that pyrolysis, but it is completely process dependent, also feedstock dependent. Therefore, we are looking into the challenges, and we already published recently very good papers on this. We are also looking into other options, like some intelligent option like hybrid nanofluid, and then the combination of phase change material in addition to this biochar phase change composite, and looking into not only these solar thermal application. Why solar thermal? Because some of these are pretty good for low thermal application, starting from maybe 60, 70, that sort of range. And also, we are doing quite a lot of work in this area, that how to better thermally manage the cooling aspect of an electric vehicle battery, which is another challenge, because for maintaining this challenge, you need to maintain a threshold like 35 degree in the battery pack, something like that. So if you go few degree plus minus, if there is a mismatch, you got thermal runaway. So thermally, there will be accidental fire. That's called thermal runaway. So we are looking into these challenges, and then by bringing in some novel concept like fin-based application in terms of designing the battery pack, okay, so next generation battery pack, and then try to optimize this, okay. Some might not be very thermally efficient, some might be, but we have good finding from that as well. So again, this is pretty much related to what we are discussing here, polygeneration, waste heat, and then how to optimize this. So I think I will conclude by just saying, okay, bringing in few more bullet points here. So in the last 1 hour, 25 minutes or 20 minutes, so I know I possibly gave quite a lot, but we primarily break down things. We primarily talk about thermochemical processes, gasifications, and then bringing in various different types of feedstock with my goal to optimize the syngas production and hydrogen production. I try to demonstrate a concept and some applications of BECCS and some of our initial work based on that. Then I did a bit of overview of some of the work based on the hydrogen end use, ammonia end use in terms of combustion, and the technology that we are working towards to meet ultra low NOx combustions, and some of the novel applications of new concept. And then these are pretty much linked to those, but it's a sort of another thermal idea. I know, and Professor Rohit Mehra also highlighted that, and if you look into the policy aspect, these need to be linked together with other like policy, social side, economic side. So I collaborate intensively with colleagues internally in business school or doing life cycle analysis. And one of the half that we mentioned, Supergen Bioenergy Impact halves, we've been working closely with some colleagues so that we can actually, not from the technical aspect, we can actually work together to combine all sort of socioeconomics under this topic. So, and in terms of acknowledgement, okay, again, I'd like to thank you, all of you, for listening me. I know I cannot see everybody there, about 126 people at the moment, but thank you very much for listening. So it has been really great speaking to you. And these are some of the funder I put there. There's some, but there might be more. I just need to review, but they provide us funding support in various ways to do our research. And there are, I have a group where we got colleagues, we got postdoc, PhD, and other research students. They work collaboratively. So all credit goes to them. So because they are the main sort of driver for the work, I support them, and also collaborator from coming from there. Yeah, thanks to everybody for listening my talk. Thank you. I think I
thank
finished.
you, Professor. Thank you, Professor Manoj Paul. Due to technical glitch, we were not able to introduce Professor Manoj Paul, expert for session 1, as well as chief guest of our inaugural program.
No
so
problem.
Professor Manoj Paul is a professor of thermofluids and deputy head of energy and sustainability research group within the system power and energy research division of James Watt School of Engineering, University of Glasgow, UK. He has been working at Glasgow for nearly 21 years, received PhD in thermofluids from University of Bath and postdoc from Imperial College London. He is a chartered engineer, fellow of Higher Education Academy, and member of Engineering Professors Council, Institution of Mechanical Engineering. He is the UK representative and the member of International Energy Associate, Bioenergy, Task 33, Biomass Gasification, and elected executive member of the British section of the Combustion Institute. His research interest includes bioenergy, including gasification, bioenergy with carbon capture and storage, BECCS, hydrogen energy, combustion, and waste to energy technology. He is also interested in solar energy, thermal energy storage, hybrid renewable energy systems, and advanced computational fluid dynamics and numerical simulation method for thermofluid research. Professor Paul has strong research output with 129 journal papers, 131 conference paper and presentations, 17 media contributions, and several contributions to books and industrial reports. He has supervised numerous postdoc as well as research associate, and he has guided 27 PhD scholars. He has also served as an examiner of numerous PhD theses. His professional engagement extends beyond research. He represents the UK on the International Energy Agency Bioenergy Task 33, and also he is an elected executive member of British section of Combustion Institute. Professor Paul is an active member of several committees, journal editorial board member, and consultancy projects. He has been recognized with multiple awards and scholarships. He has delivered many invited talks, and visited various institutions as a visiting professor. So we are truly honored to have Professor Paul with us. Very thankful. We are very thankful, Professor Manoj Paul. This is an absolute honor and privilege to extend heartfelt vote of thanks to Professor Manoj Paul for his invaluable contribution to today's session. Sir, your insights and expertise has provided us with a deeper understanding of biomass gasification in combined heat and power plant. Your ability to convey complex ideas in such a clarity has truly inspired us. The knowledge and experience you have shared will definitely leave a lasting impact on our academic as well as research pursuits. On behalf of everyone present, I express my deepest gratitude to your presence and enlightening sessions. We look forward to more such opportunities to learn from you in the future. So thank you once again. So now, if anyone from participant side, if you have any doubt, please you can write on the chat box.
I also would like to thank you and Professor Srinivas and all the organizing members for inviting me to give this talk. So again, it has been a pleasure for me. So you have a very beautiful, beautiful and also engaged session also coming in the next few days. So I hope that you'll enjoy and everybody will enjoy the interesting session that we have. So thank you once again for your for this opportunity. And yes, if anyone wants to discuss any research opportunity or have any questions, please drop me an email at any time. Okay, so it would be great to hear from you.
Thank you, sir.
Sir, last question.
Yes,
Indeed,
please.
yeah.
Yes, sir, yes.
Sir, what is the full form of HTSG and HTAG?
Sorry, can you?
What is the full form of HTSG and what is the full form of HTAG?
So on which slide number you are asking?
I'm
Sir,
sorry.
on part A, sir, biomass gasification in combined heat and power, the links you have given that is blue and green, sir. By indication of blue and green, for that purpose I have asked, sir. Yes, sir.
Yeah.
All right. Okay. Yeah. I should have actually put some note here. High temperature steam gasification. Okay. So usually you get steam gasification.
Steam gasification.
Okay.
Yeah, and this is high temperature air gasification. Okay, because
Sir,
you could air.
Air temperature. Okay, sir.
Okay. Yeah.
Okay,
so
sir.
next time I'll put a note here. Yeah. So
Sir,
because if you
one more question, sir. Last question. Sir, you have said
Please.
ultra low or zero NOx will be affected to the environment, sir. Yes, sir. Ultra low or zero NOx catalytic burner will affect the environment, sir.
No, because you are trying to get almost zero emissions of NOx from a system. Therefore, that is the ambition. Now, how to get there, that's a challenge. So that's what I'm trying to understand. Okay.
Hello, sir.
Thank you, sir.
Hello, sir. Myself, Dr.
Yeah, please.
I basically belong to mechanical department, but from my MTech to PhD, I have studied interdisciplinary. Now I'm also teaching in interdisciplinary branches, from mechanical to petrochemical to plastic branches. In our college.
Sorry, can you speak a little bit loud? Can you speak a little bit loudly? Yeah.
I am saying that here I am working in CPET Jaipur, which is a IndustryCom Institute Center. Here basically we test the plastic material, and we have also one pyrolysis plant, pyrolysis plant. How is it different? Basically, I belongs to mechanical engineering. I don't have much in chemical related stuff. Sir, how it is linked the gasifier with the pyrolyzer?
All right, okay. I'm also coming from mechanical engineering perspective, so I'm not a chemical engineer, okay? So I sit at the interface between mechanical and chemical, although I bring a lot of chemistry in there, right? So basically, in the pyrolysis, typically we say we want to actually convert solid to either in a solid form or liquid or gas in a starving condition. So we don't provide any sort of air inside this pyrolyzer. Gasification is a similar thermochemical, but you bring some agent, whether you want to do air gasification or steam gasification, and then you aim to generate more syngas because you want to break down the solid, okay, to gas. So this is basically the fundamental difference between a pyrolysis process and the gasification process. Does that answer?
Sir, this is your last question, sir. I'm from Sona Project Technology. Sir, can you compare updraft and downdraft gasifier for syngas production as well as for char formation?
If you are looking into gasification in a downdraft gasifier, the first thing, you don't want to get char because you want to convert all char to gas, okay? Therefore, I don't think you can compare two things together, okay? Because your aim is to convert all the solid to gas. So you want to minimize to have any sort of residual char in the reactor. I know this is ideal, but you really want to get a late char because all these kinetics here, this char is decomposing to gases. So you need to make sure this occur in the reactor, irrespective to the reactor design, whether downdraft, updraft, or any other fluidized bed reactor. That is actually the aim here. On the other hand, pyrolysis, as you know, you want to convert your feedstock to a good char in sort of slow process, and therefore I don't think you can compare these two together, okay? However, in some feedstock people use, we also trying to explore that if you want to pre-process, okay, some feedstock, you can use little bit of pyrolysis technique in order to just increase bit of I think feedstock, we say preparations before you put that feedstock in the gasifier. That might, later I said that data is also available that it could actually improve the reactivity that way, okay? So that's why I'm saying that two things cannot be compared because two things coming from two different objective.
Sir, in terms of production rate, which one will be better? Syngas production.
Oh, right, okay. It's obviously gasification because gasification gives you more syngas. Pyrolysis will not give you that.
Thank you, sir.
Okay.
Okay, so anyone else?
Okay. So that's, I think we are done, yeah? All right then. So I believe you now have the next talk to move to. So
thank you, Professor Manoj.
Again.
Thank you, sir. Thank you for
no
this
problem.
talk.
Yeah, so it was pleasure. So thanks once again. So enjoy rest of your event and also the other talks for the next few days. Thank you very much. Okay, everybody.
Thank you,
bye
sir.
then. Bye.
Dear participants, next section 2 we are going to start in 2-3 minutes. Please wait for 2 to 3 minutes.
Sir, can we have a 5 minutes break?
Yes, you can take 5 minutes. Okay, fine. No issue. Yes.
Yes. So again, we are thankful to Professor Manoj C. Paul. So now I would like to request Professor T. Srinivas to invite and introduce next expert.
Okay, thank you, Dr. Rajan. I will continue this section too. I think I'm waiting 2 to 3 minutes. Professor B.V. Reddy is joining to deliver the talk.
Sir, we will take 2 minutes.
Yeah, okay.
No, are you able to see me? I am already on the link.
Yes, sir. Welcome, sir. Welcome.
Okay.
Sir, we gave that gap, so that means 5 minutes gap to the
I
participants.
heard no problem. No problem. I'll wait. Okay.
Yes.
Since I joined, I'll wait on the link. Yeah, that's okay.
Yes.